Hello viewers, welcome to our science lesson. I'll be your presenter, Buba Tamba. In our today's lesson, we'll be looking at the basic definition for physical and chemical changes. In our day-to-day life activities, of course, we undergo through certain activities. Whether we realize it or not, of course, our activities influence these type of changes that we normally live through. And the main two types of changes that we go through on a daily basis are physical changes and chemical changes. In a nutshell, physical changes are the type of changes in which no new substances are formed after the change. However, in chemical changes, these are the type of changes in which new substances are formed. Physical changes are not easily reversible. However, chemical changes, of course, physical changes are easily reversible, I beg your pardon, but chemical changes are not easily reversible. So we go in depth and look at take a few definitions, of course. The first definition that we will be looking at will be physical change. And like I said previously, physical change is a change in which no new substance is formed. It is reversible. Example, melting of ice. Now, if you look at the screen, what you have there, of course, these are samples of ice cubes being melted. So this is something that normally confuses students. Melting, of course, of ice. There is another scenario that includes melting of candle. And that is the very one that normally traps students. Melting of candle and burning of candle. The two are different. One is physical change and the other one is chemical change. Now, if you look at chemical change, like we said in the beginning, is the type of change in which a new substance is formed. It is really not easily reversible. Because when you move from the original substance and now you form a new substance altogether, it is normally impossible to go back to the original substance. And that is what we call a chemical change. Examples of chemical change include burning. When you burn something, obviously you are transforming that material from its original type into a new substance altogether. If you burn wood, you burn paper, you burn charcoal, for example, obviously you are transforming the material from its original form to another. Okay? We'll also want to look at elements briefly, and we say by definition it is a substance that cannot be decomposed into smaller substances by ordinary chemical processes. Elements are the fundamental materials of which matter is composed. Right? We'll also want to look at mixtures. And in our today's lesson, our focus is really going to be based on mixtures and how do we separate mixtures into their components. So first, what is the definition of a mixture? A mixture, by definition, is a substance that contains two or more elements that are physically combined. Example, air, for example, is a mixture. Seawater is a mixture. Soil is a mixture. Crude oil, milk, sand, and water, of course. These are all mixtures, right? And now you want to look at compounds. A compound is a substance consisting of atoms or ions of two or more different elements in definite proportion, joined by chemical bonds into a molecule. For example, you want to look at a compound of ammonia, for example. You want to look at a compound of water. You want to look at other compounds like carbon monoxide. These are all compounds, for example. Right? Now, the elements of a compound cannot be separated by physical means. Water, for example, is a compound having two hydrogen atoms and one oxygen atom per every molecule of water. Now, after we have briefly discussed or defined these various substances, and of course their shapes and stuff, we now want to look at properties of mixtures. What is a mixture? What are the properties of a mixture? What physical characteristic would you see and obviously attributed to what is called a mixture? So that is what is called properties of a mixture. Those properties are what we want to look at. Number one, they can be separated by physical means. So that means if you have a mixture, for example, you mix groundnut and maybe some rice grains. If you mix them together, physically you can separate them. So that is what is called a mixture, for example. If I take apples and bananas and put them together, obviously I can physically separate them. So that is what is called a mixture, right? Number two, we say the properties of a mixture are the same as the properties of the elements which they are made of. So if you have elements forming banana, and you have now other elements forming, let's say, apples. If you mix these apples, obviously, the elements of the mixture, the properties of the mixture obviously are the same as the properties of the elements that actually form that particular mixture. That, in a sense, is what we are trying to explain here. Now, we say heat is not usually involved when a mixture is made. Naturally, if I pick up a number of apples and bananas and mix them up, obviously, I'm not introducing any heat. So that is just a mixture, a simple mixture. The elements in a mixture are not in a definite proportion by mass. What we mean is, like, for example, if it is a compound, for example, obviously the elements in that particular compound are there in a proportion, in an accurate proportion by mass. Like, for example, if you look at water, 2 atoms of hydrogen combining with an atom of oxygen to form water, right? But when it comes to elements, when it comes to mixtures, that is not the case. I can take 3 different apples and mix them with 5 or 100 different bananas, and it's still a mixture. I can take 1,000 different apples and mix them with 200 bananas, and it's still a mixture. So you see, they are not really in definite proportion by mass. Now we want to look at the methods of separating these mixtures, because now we have different forms of mixtures, right? And depending on the type of mixture that you have at hand, that will dictate what type of separation technique you are actually going to use to separate this type of mixtures. Now, for example, if I have a mixture of, let's say, oil and water, or kerosene and water. If I have a mixture of kerosene and water, you know, these are 2 different liquids. Water is a liquid of its own. It has elements that actually form it. And kerosene also is a substance of its own. It has its own elements that come up to form kerosene. And now you mix these things up, liquid. How do you go about separating them? Obviously, it's going to be different from when you mix apples and bananas, or when you mix charcoal and, let's say, some sort of grains or whatever. It's going to be different because the type of mixtures that you are dealing with are different, right? You're dealing with a mixture that is in a liquid form. You're dealing with other mixtures that are, of course, in solid forms, and other liquids that are in powdered form. And obviously, it's really going to be different. The methods are going to be different, right? So the first thing that we are going to use is called separating funnel. Separating funnel. And this basically is when you have 2 different liquids, and you want to separate them into their various components. Now, if you look at this, this is a separating funnel or burette. In the event you don't have a separating funnel, you can use a burette in your school. If you have a burette, I think most of the schools really have burettes. If you don't have a burette, you have a separating funnel, obviously you can also use that. It's still the same. You can also improvise. You can even use Evian bottles, and you just pipe it. You connect a pipe to the mouth, and you have a way of sealing it up, of course, and then you have a way of fixing a tap to the pipe, and then you introduce the liquid in the Evian bottle, the substance in the Evian bottle, the mixture I mean, and then you allow the tap to flow. The liquids are obviously going to settle based on their density. This is a very important point that every student needs to know. How are the liquids arranged? Liquid mixtures, how are the various components arranged in that particular mixture? Obviously, they are going to be on top of each other. Based on what? Based on their densities. That is very important, based on their densities. So by definition, we say this method, or by explanation, we say this method is used to separate 2 immiscible liquids that are not chemically combined. Example, water and oil, water and kerosene, obviously, right? And that will lead us to our very first experiment. Now this experiment, we will need a separating funnel. I will show you what a separating funnel is. You will also need, if you don't have a separating funnel, you can use a burette like I said initially. You could also use kerosene. If you don't have kerosene, you can use oil. If you don't have kerosene, oil, you can use any other different substance, different from water. Well, if you use water and water, obviously, these are just the same substances. Any other substance different from water, actually. And you would also need water, you would need 2 beakers. Now I will show you this. You would also need a retort stand. Now this is what is called a separating funnel. This is what is called a separating funnel, right? This is where the opening is. This is where you introduce the substance. This is where you introduce the substance. and that is the tap. The tap. This is the tap. This is what allows the liquid to flow out. And if you want to close it, you can also close it. When you turn it this way, you are opening it, and when you turn it that way, you are closing it, right? And that is the stopper, or the stopper. This is what closes it up. That is what is called a separating funnel. If you don't have that, you can use a burette, which is a bit far from me right now. And this is a retort stand with clamp. That's the clamp, and that is the retort stand. And that's the base of the retort stand. I hope all of you can see that, right? Okay. It says set up the apparatus as shown in the diagram above. And which is the diagram above? That is this diagram that you are seeing, like I explained. It says set up the apparatus as shown in the diagram above. Mix together equal volumes of kerosene and water. So this time around we are going to use kerosene. Unfortunately, kerosene is not readily available with me. So, but I have oil. So I am going to use oil instead of kerosene. Still the same, no problems. If you have kerosene, you can use kerosene. If you don't have kerosene, it's fine. But you have oil, you can use oil, like I said in the beginning. Pour the mixture into a separating funnel or burette. Let it stand still for about 30 seconds to allow the liquids to settle. 5. Open the tap of the funnel or burette and collect the liquid separately in different beakers, right? And then we will ask a question, what have you observed? Or maybe I should just go step by step, right? So the first thing that we are going to do is we are going to mount our separating funnel on our retort stand. We do this gently because these are fragile materials. When they fall, they break. This is vegetable oil. So that is what we are going to use. So the vegetable oil, let's say maybe we measure 20 mils of the vegetable oil, and also maybe 20 mils would be small. We can measure even up to 30 or so. Yeah. No, it's not there. Yeah, so that is 30 mils of vegetable oil. So what we do is we pour that in the separating funnel, gently and carefully. Okay. We do the same for water. You can see they are even different. They don't even look the same. Water too, we measure, let's say 30 mils of water. The quantity really doesn't matter that much. Okay, so now it was the vegetable oil that we first introduced. Now we are going to introduce water into the separating funnel, and we allow the liquids to settle down. Now watch what happens, because I am going to ask you a question. Okay. Now watch what happens. Which one can you say is denser than the other? Deliberately, I'm going to shake them somehow. Going to shake them up. And you can still watch what will happen. Still watch and tell me what happens. So now, I have a question, and the question reads, what have you observed in the different liquids? What have you observed in the different liquids? What have you observed in the different liquids? Can you tell me what you have observed? Can you tell me what you have observed here in the different liquids? So you can clearly see that the liquids are obviously not mixing. They are not mixing, and they are settling down based on their densities. And you can see them also differently. The water is the more transparent one, and of course the one that looks yellowish in color is the oil, right? Now the different liquids are not on top of, the different liquids are on top of each other according to their densities. Now what is the density of oil? So you have different types of vegetable oil. In some cases you would see 0.21 grams per cubic centimeter, and average up to 0.78 or 79 grams per cubic centimeter. However, water is just 1 gram per cubic centimeter, or 1,000 kilograms per cubic meter. And for the case of kerosene, which we actually have on the slide, is 0.78 or 0.8 grams per cubic centimeter, which is around 800 kilograms per cubic meter. 800 kilograms per meter cube. Yeah, per cubic meter. It's all the same, right? So that is what we have. So based on their densities, now if you look at oil, for example, if you take the density of oil to be, let's say, if we take the density of oil to be, on average, let's say 0.21 grams per, let's say, grams per meter cube, and that of water is, let's say, 1 gram per meter cube, 1 gram per meter cube. So if you look at the two densities, because we know, according to the law of nature, that substances would always settle based on their densities. That is a natural law. If you're traveling with your sister, there's only one position in the vehicle and you are two in number, and you are heavy, your sister is small. Who would carry the other? I think the heavy one will carry the lighter one. So you normally carry your sister. Yeah. So if you have water as 1 gram per cubic meter, and you have oil, vegetable oil, 0.21 grams per cubic meter. Sorry, this cannot be cubic meter, per cubic centimeter. I'm sorry about this. So we will have to change that. And we will change it, let's say 0.21 grams per cubic centimeter, and this is 1 gram per cubic centimeter. So obviously, if you have something like this, which one would settle on top of the other? Obviously, we see that the water is heavier than the oil. So obviously, the oil will be on top and the water will be at the bottom, just like you have in the separating funnel there. The water is on the bottom and you have the oil on top. So based on this, and that is why this point is saying that the different liquids were on top of each other according to their densities, because the density of water is larger than the density of oil, right? So that is what we have. And now we can conclude by saying, because we have already investigated this, so we can conclude by saying that immiscible liquids can be separated using a separating funnel. And that will bring us to the end of this particular exercise. Now we are going to separate them. As you can see, the different substances have settled based on their densities, and of course the color even is a distinct factor there to tell you that the upper part is obviously the oil, and the lower part, which is more transparent, is the water. Right, so we're going to open our tap and we watch what happens. Now we try to collect the water. Oh. Okay, just about 40 grams or a little above 30 mils. I think that some oil must have escaped and gone in. And now we want to collect the oil itself. Okay, so that is it. That is the oil, and that is the water. So clearly, you can see that we were able to separate the different substances using a separating funnel. This is the water, and that is the oil. These substances can never be able to mix together. They can never be able to mix together. They can mix actually, but they will not be able to do what is called a chemical change. The change that occurs after they mix is called a physical change, but it can never be a chemical change. Because that, after they have mixed, you can always separate them using either a separating funnel or a burette, right? So that does it for this lesson on separating techniques or separation techniques, right? For the first, obviously, that we took is the use of a burette to separate two immiscible liquids. That is the very first one that we took. And we are going to look at now, we are going to look at evaporation, right? We're going to, okay, huh? Oh yeah. Yeah, so hold on, let me take it again. To move to the next separation technique, and that is evaporation, right? As you have seen on the board, evaporation. Now, for example, if I have a substance or a mixture of, let's say if I have a mixture of water, or let's say if I have seawater, for example, seawater. You know, seawater is a mixture of water and salt, right? Or I just deliberately pick some salt and introduce it into a beaker containing water and mix them up. Obviously, the salt is going to dissolve in the water, and there is going to be what is called a salt solution. Now, when that happens, and you want to now separate these two into their various components. For example, you want to have the water on its own, and you want to have the salt on its own, right? What you can do is you can do what is called, there are different methods you can use, but in our case for today, what we are going to do is called evaporation. And in that we are going to introduce salt into water, for example, and we have a salt solution, and then we mix them up, we stir until the whole salt is dissolved in the water, and then later we would place the water in the sun and allow it to evaporate. If you don't have, if you cannot use that, you can also use a Bunsen burner, for example, to fasten the process. You can also do that. So in our case today, we say evaporation. Excuse me. We say evaporation. This is the method used when one element of a mixture is soluble in water. For example, salt and water, right? For example, salt and water. And that is going to lead us to our second experiment. And in this experiment, like I just explained, we will be needing a beaker, for example. We will need salt, we will need water, we would need a Bunsen burner, we would need a tripod stand, and also a wire gauze and a stirrer, right? Those are the things that we will be needing, right? And according to the procedure would be like, number one, according to our procedure, we say mix about 20 grams of salt in that's 1/4 of a liter, in 0.25 liters of water in a beaker to get a salt solution. Number two, pour part of the solution into a beaker. Number three, leave the solution in a sunny place for about 2 hours or heat it with a Bunsen burner for about 10 minutes and observe what is left in the container. As simple as that. So we are going to set out ourselves into doing this particular experiment. Okay. This is our beaker. This is also another beaker, but this one has salt in it. So what we will do is we are going to introduce 20 grams of salt in 0.25 liters of, okay. Yeah, so that's our water, and now we need to measure this. That is our spatula. So now, this is what we are going to introduce into our beaker of water, and we will now go and heat it up. So that is our stirrer. This is what we are going to take and mix the salt in the water to make sure it dissolves completely. So now that we have, this is called a salt solution, right? Now we want to recover the crystals of salt that actually were introduced into this beaker. How do we go about that? What we will do is we are going to place it in the sun and allow it to evaporate. We'll place it for about 2 hours. That will allow, or even more, that will allow it to evaporate. But because we don't have the luxury of time, what we are going to use is to use the Bunsen burner. That is going to help the process. That is going to fasten the process, right? So we are going to place it on the Bunsen burner. We're going to place it on the Bunsen burner here. That is our Bunsen burner. Okay. Okay. So we would allow it to heat up, and all the water will eventually evaporate. And the water is evaporating, and the crystals are being formed on the side of the beaker, as you can see. These are crystals of salt. You can see them. So if we allow the whole of the water to evaporate, all that we will be left with will be the crystals of salt, the salt crystals. Right? So now that we have done the heating, and all you can see is basically, you can see crystals. You can see crystals. These are crystals of the salt that initially formed. You see, this is crystals. Right? So the water has evaporated, leaving behind the salt. So this way, we can also separate a mixture of salt and water. Even if you go to the sea, you collect seawater, for example. Seawater is a solution it's a salt solution. So if you collect it, obviously, and that's the local, that's what our people do in the villages, obviously, in salt processing. That is what exactly they do. This is exactly what they do. But normally, for them, they don't use heat. They use the sun. The heat, they don't use Bunsen burners, for example. They don't use fires, but they use the sun. But then the process is still the same, right? What they do is to evaporate the water, and they collect their salt. So this is another method that we can actually use to collect. This is one method that we can also use to separate a solution that contains salt and water. So you can see we have fully recovered not actually fully, but we have recovered the salt that was actually used in the preparation of the salt solution, right? So in the observation, we observe that only crystals of salt are left in the beaker, which is really true. If you look at this beaker, only crystals of salt are left in the beaker. Look at the beaker properly. Only crystals of salt are left in the beaker. Can you see that? Yes, only crystals of salt are left in the beaker. Now, conclusion, we can conclude by saying that evaporation technique can be used to separate a salt solution into its component. What are these components? Of course, they are salt and water. Unfortunately, in our case, we could not actually recover the water. because we are using the technique of evaporation. If we want to recover the water, obviously we could have condensed the water somehow and have a way of collecting that water too, which is going to be explained in another experiment. So I thank you for your kind attention. I'll see you in the next video.